Assalamualaikum and have a good day to all the panels. So my name is Muhammad Zahirrudin bin Yunus. I came from KL 201/05. So today I want to present my FYP final year project. It's about analyzing sound synthesis using finite difference method. So the first one is about introduction. Okay, for the research background. In mathematics, they have two methods to find the solutions. So it's about there is analytical and numerical solutions. So for analytical is to find the exact solution, meanwhile the numerical to find the approximate solutions. So for finite difference methods, there is numerical techniques for solving differential equations by approximating derivative with finite differences. FDM can convert to ODE or PDE, which may be nonlinear, into a system of linear equations that can be solved by matrices and very useful for extrapolating a finite amount of data in an attempt to find the general term. Okay, for the sound synthesis, they have several types of type and method of sound synthesis, which is subtractive, frequency modulation, wavetable, physical modeling, additive, sample and synthesis, phase distortions. So for this analyzing, we are using the physical modeling methods. For the problem statements, this FDM is competent to solve the wave equations. So the second one, analyzing the sound synthesis by using FDM based on physical modeling is manageable. And the last one, there are too many musical instruments with string have vibrational properties like any other vibrating structure. Research objective. The purpose of this project is to apply finite difference method in analyzing sound synthesis and to seek the sound synthesis in musical instrument. The significance of project focuses primarily on the physical modeling of musical instruments used in sound synthesis and musical acoustics, and determine the ideal string equations for the musical instrument by evaluate the modification to the strings equations. For scope of project, the wave equation is used for model study. The easiest vibrating string in mathematical model by using wave equations. Changes of the tension, the size and the weight of string related to vibrations. So the next chapter is about literature review. As we can see, there are three types of numerical solutions, which is finite difference method (FDM), finite elements method (FEM), and finite volume method. So you can read the table for the advantage and disadvantage. Like I said in the introduction, so the sound synthesis categorized by four, which is sample based synthesis, synthesis on abstract method, synthesis signal modeling, and synthesis on physical modeling. For the musical instruments, I chose the plug string and the struck string. So the plug string, this is the general equations for the plug string. And the second one is about struck string. So this is the general solutions, general solution for the struck string. Okay, then we go to the methodology. As we can see, the equation that been shown is an example of PDEs. So this is the partial derivative of PDEs. The UT, UX, UT, UX, and UYY. This is about the second derivative. Generally, classification of PDEs have been give three, is elliptic, parabolic, and hyperbolic. So we use the hyperbolic to achieve the wave equations. This is the boundary condition and initial condition. So later we are going deep about these BCs and ICs in implementations. So next we are going to Taylor's theorem. So as we can see, the Taylor's theorem, or we can call it Taylor series expansions. So from the Taylor's theorem, we are neglecting the higher order and we neglecting the expression of OH, because OH is the constant term. So the expansion of Taylor's theorem, we get this expansion, this equation. Okay, just now I said about the OHN. So this is the meaning of OHN. Okay, then this is the description and characteristic of order OH and power of n. So there are 1, 2, 3, 4, 5 characteristic. Okay, we are going to the implementation. So the slide is talk about derivation of wave equation. So this is the string that been stretched along the x-axis and x-axis. So the small transverse disturbance along y-axis and AB element of displaced string. This one. So from the stretched string, the tension T at A, just we see the figure along AA is about T sin theta approximate T tangent theta. So same goes to tension B along BB, T sin theta plus delta theta equal to T partial over the partial x, partial y over partial x. So the next force standing displaced delta L this is the expressions by using Taylor series expansion that we've been talk about at the methodology. So we get the del Fy, then neglecting the higher order, just we say the higher order, then we get the del Fy, this one. Then from the Newton's law physics, del Fy, so we can get the tension. Then the wave equation, this one, this is the wave equation. So the C determined by tension over mu. So C is velocity of transverse wave along the straight string. Okay, next part is about solution of the wave equation. So just now the wave equations, the general wave equation is come from PDE. So substituting the yxt equal to fxgt in wave equation and dividing the fg. Okay, and this is the wave equation. This wave equation can be solved by separation of variables. So by separation of variables, so we get the equation, this one. So we need to divide by left and right. So the left hand side we get this expression, and the right hand side we get this expression. For the k, the constant is omega n over c, the velocity just now. So the general equation to this equation, we can achieve this one. Okay, then the solution of wave equation from all the calculation, these equations, these wave equations. Let's see the example. The string fixed at both end. This one, both end. Okay, then the basis, the boundary condition F2, which is y equal to 0 at x equal to 0, and y equal to 0, x equal to L. Okay, this one XL. So for boundary conditions, for the first boundary condition, y equal to 0 at x equal to 0, we substitute the boundary condition in the general solutions. So we get the solutions. And for the second boundary condition, we substitute the y equal to 0 and x equal to L, and that is the second solutions equation. Okay, then the constant k and L is equal to n pi, and n is any integer must not less than 1, which is the 0 and go to the negative. Okay, then the solution will becomes this one. Okay, this is the solution for the wave equations. After we get the solution, so the solution have to get into the sum. So this is the general solution obtained by principle of superpositions. And the an is equal to Cn cos phi n, and the Bn is equal to Cn sin phi n. So we can substitute this from this Bn to this one. Okay, so this is the solution, the final solutions. Okay, for the next is about plug string. Okay, plug string. So basically we need to know the initial condition for every equation. So for the plug string equation, the initial displacement at any point is equal x equal to y0, and the initial velocity at any point is 0 y dot equal to 0. Okay, so this is the initial conditions. 2. So the general solution that we obtain by the principle of superposition, we insert the initial condition for the plug string. So the y dot x comma 0. So we get the solution. This one. This is the solution for the first initial conditions. Then for the second initial conditions, this is the general solution. So we get the general solution by inserting the second initial conditions. So an can be determined by Fourier series. So multiply both sides by sin knx and integrate the over string. So this one we need to integrate both sides. Then this is equation. If n not equal to s, so this equation will be 0, and if the n equal to s, there will be L over 2. This one L over 2. Okay, then the es, we need to rearrange the these equations from the previous equation. So the as will come out with 2 over L, and this s we need to substitute to the n back. Okay, and back. So from the previous equation we need to add the two equation that we've been solved. So the two triangles, this one for the small triangle, that one is for the big triangle from the right triangles, and we do the integration by parts. So this is the equation for integration by parts. Then the solution for plug string is, this is the solution of plug string, and substitute back the kn and omega n. Okay, this is the solution for the plug string. Next we go to the strut string. Okay, this is the hammer that knock the string. So the initial condition not same for the plug string. So the displacement at t0 at point x equal to y, and initial velocity at t0 at any point 0 at such a small string. So from the general solution transverse equation, we insert the initial conditions. So by inserting the initial condition for the first initial condition y x0, so this is the equation, and the solution we get this one. Okay, and the inserting insert, we substitute the second initial conditions. So the second condition, y x0 equal to y naught dot. Okay, so the Bn, this Bn can determine by Fourier series methods, and same goes to the plug string. So we need to multiply both sides and integrate the over the string length. Since the n not equal to n not equal to s, so we get the 0. So I need this one n equal to s, so we get the L over 2. Then we need to do the integration by part. So we get this is the after the integration by part. So the substitute n to S and LA plus DA. Okay, then this is the solution for the BN. So the final solution for start string, this is the final solution, and we need to substitute the Kn and omega n. Okay, this is values of K and this is the final solution of start string. So next we go to the result and discussions. So result, we take the example of two sounds, which is the guitar and piano sounds. So as we conclude the final solutions, this is the final solution from the separation variable that we solved just now. So the Kn, okay, there's the equation just now we get it, and plug strings and the start string. So for the first histogram on both strings, so this is the histogram graph for the both. So this is for guitar and this is for piano. So the figures 1 and 2 show the value of the amplitudes. So we need so this is the amplitude axis, then the x-axis is time taken. So the histogram was running by MATLAB coding. So this shows the highest peak of both sound, so which is concentrated around the zero value. So the two histogram this zero value, and this kind of sounds is normalized signals. Next we for the signal in time domain, so the guitar at the left side and piano is the right side. So same, it shows the amplitude for both sound is given x as time step, and the time domain has take. So this is time taken, we take as 5 seconds approximately. So y-axis is amplitude, and the piano is the amplitude. The peak of amplitude of for piano is less than guitar, and for the amplitude is related to harmonics. So whenever the amplitude is sound higher, then the harmonic will be there for in the string. So the 5.4 periodogram on both string, so the guitar and piano. So you can see the guitar periodogram and piano periodogram. So the x-axis show the frequency, this is frequency, and the y-axis is a power content. Okay, power content. So approximately at 13 kilohertz, yes, 13 kilohertz this one. Okay, 13 kilohertz for both sounds. Okay, but for both sound indicate there is negligible power because the is below zero. Okay, so the spectrogram on both string, so this is a spectrogram. As figure 1 and 2 shows that spectrogram function that display the signal in time frequency domain. It shows that frequency of the vertical component varies as a function of time. Okay, so this is the times taken, or no, this is the power of power content. Okay, and notify that guitar shows the upper half of spectrogram from 13 Hz approximately, and above is the lowest power level. Meanwhile, the piano shows that from 4 Hz approximately above has the lowest power level. Means the piano has the lowest power level than the guitar. So the sound of guitar and piano was taken for 4 seconds. So the conclusion and recommendations. So this is plug string, and second one is start string. Okay, so you can read about the slide. So the conclusion, the musical instrument that involved in this method are piano and guitar. For piano is striking the string, and for the guitar is plucking the string. Then the piano more harmonic than guitar. By using MATLAB, we can compare between the start string and plug string. As for the future application purpose in mathematical science field, it is recommended to use FDM in solving the wave equation. Okay, on top of that, it also suggested to apply the FDM in one-dimensional cases.